So, yes, good evening. Good evening from the Netherlands. This is our monthly meeting on the transformative vertical flight, public services. It is today, Thursday, June 19th, 2025, and we are going to start our meeting. My name is Marija Popovic, and I am co-chairing this group together with Johnny Du. Johnny is not online this evening, so I will chair the meeting. And we are going to start first with our usual events. So let's try to see what are the events going on at the moment on the advanced air mobility. And I put some of them, and the first one that I put you here is the Paris Air Show. Because from 16 to 22nd of June, we have the International Paris Air Show. And it's annually and famous, the biggest air show, I think, in Europe. And I looked at the program, and for example, I saw that there is going to be a very extensive Paris Air Lab on innovation on sustainable air transport. There is going to be an Start Me Up, a very big event on startups who are working on the area of aviation. And there is going to be as well a kind of competition on the drone saucer, which is kind of Harry Potter play. And I understood, I don't know, I didn't know, but this is an interesting, fun flight and future. So that is an air show. I haven't been this year to the Paris Air Show. I think last time I was 5 years ago. So I don't know if somebody from Masha, you haven't been as well to the Paris Air Show, no?
No, I haven't.
No.
I've just heard of it.
Yes, you should see once. It's very interesting. It's very big and interesting. Another event that I know of is the EAT conference. And this is an interesting conference. Is on Electric Aircraft Technologies Symposium, which is this year together with the IEEE Transportation Electrification Conference. So it is between 18th and 20th. So it's a very important, it's a conference on mostly electrical engineering and future electrification of aircraft. Very interesting. And I put now in July the Electric Aircraft Symposium in Oshkosh, which is probably going to be attended by some people in this meeting. Do you know some other events which are placed in June? Ben, you were talking of some event.
Oh, well, no, here in Australia, there's a regional aviation event that I'm at. And that electrification just before Oshkosh is very popular. I know that my founder, Michael, will attend, and I think you guys know Andy Mearns, he'll attend. That's a big electrification event. And it just precedes Oshkosh the 2 days before.
Mm-hmm.
So they've scheduled it so you can still get into the cheap hotels. Because once Oshkosh starts, there's no cheap rooms.
Okay, yes. No, never been. I would like to go once to this event. So hopefully in the future we can travel
Me
more.
too.
Yes, you too, as well from Australia. It's more
Me
difficult
too.
for us as well from Europe. It's more difficult. Those are the events that I put. I do not know if there are some other events. Probably there are some. I know September it will be European Rotorcraft Forum. I attend always European Rotorcraft Forum every year. and VFS, so more of a Rotorcraft community. And this year we'll be in Venice, so that's a nice spot. And there must be some other conferences going on this summer. So that is the event. And now let us try to go to the presentation that we put for today. And I would like to introduce you my colleague, Marija Popovic. And Masha is a colleague of mine. She is assistant professor at Aerospace Engineering in Delft, Faculty of Aerospace Engineering in Delft, in a group of control and simulation. She is part of the Micro Air Vehicle Laboratory, and her research is really on robotics and AI. She's active on active sensing, mapping, computer vision, and machine learning. She obtained her PhD from ETH in Zurich. She worked on environmental mapping and informative path planning for UAVs. Afterwards, she continued as a postdoc at the Imperial College in London. And she joined with us not long ago, 1 year ago. So we are very happy with her. And she was kindly to give for us a presentation this evening on her current activities. So, Masha, please, the floor is yours.
Thank you so much. Before I start, because you were talking about events, I just remembered there's a big robotics conference on the 21st to the 25th in LA. I know that this is like a US-based group, so I just wanted to like throw that out there. It's mostly like systems stuff, quite diverse, but yeah, that's happening this month, like in my community.
Yes. Okay.
And now I will share the presentation. Let's see. I haven't used Zoom in so long because we
Yes,
use Teams,
we use
right?
only Teams in Delft.
Yeah,
Yes.
but I have to say I prefer Zoom. It's like easier to adjust everything.
Yes, thank you. We see
Yeah,
it.
can you see that?
Yes, we see it.
Okay, perfect. So I'm happy again, thanks for the introduction. I'm really happy to present my work on adaptive informative path planning using UAVs. So I work on small drones like the one that you see here on the picture. A lot of my work is especially in agricultural applications because that is the institute in Germany where I was previously. They did a lot of work on UAVs scanning plants and so on. So a lot of the examples are from this domain. And I think we're in different fields a little bit. So I work really on like computer science, algorithms, learning, reinforcement learning, active learning. So I'll try to explain things as best I can to like bridge the gap here. But first, before we get into the research part, I wanted to just introduce myself because this is the first time I'm meeting everybody. So in case you can't see me well on Zoom, I just put this picture here from a conference, a big robotics conference, ICRA, that was last year in Japan, where I'm with this humanoid robot and having a lot of fun. And as Marilena nicely introduced me, I just wanted to share also where I came from and the journey that took me here. So I was born here in Eastern Europe in Serbia. And then my parents relatively soon immigrated to Russia, to Moscow. And then they actually got relocated to Abu Dhabi, where there's a lot of also robotics, AI stuff happening at the moment, but I did grow up there. And then I went to the UK to do my master in engineering at the University of Bath. They also have quite a strong aerospace department. I did my PhD in Zurich, as Marilena introduced, and over here I started to specialize more on like the algorithm side of things, computer science, and working with drones. And here I was also involved in a big EU Horizon 2020 agricultural project. Then I went to the 1 year of postdoc in London, which was not that fun because, as you can see, it was 2020 and we know what was happening then. Then I went to Germany, quite close to the Netherlands, to the University of Bonn, and here I started my research group. So I had like an assistant professor-like position there for 3 years. And finally, I moved to Delft last year, and I have now a permanent position. So I hope that I don't have to move much anymore. So that's the story that brought me here to giving this talk to you. And I also wanted to introduce my PhD students on this picture. So I have still 2 students from Bonn. Actually, the second one, he just graduated last month with great results. So I'm really happy. And Moji on the right is my new PhD student in Delft. So he started in November. And then beyond that, I also really like to collaborate with people abroad. So I have a lot of collaborations, for example, project with the University of Lincoln and some joint work with Bristol. I have a good relationship to colleagues at Stanford University, so we wrote like a survey paper on this topic together and now co-supervising master thesis. So if you do see some overlap, feel free to reach out. Okay, so now I want to motivate the problem of autonomous behavior for drones or UAVs. So first of all, why do we care about UAV autonomy? Well, here we see examples of different scenarios where tasks are done by humans manually. And in these applications, we know that drones can make things simpler, faster, and more effective to save us time, money, and labor. However, we also know that making robots work in the real world is quite challenging. So if we really want autonomous operation with minimal human input, the drones need to reason about their surroundings, make decisions about what to go, where to go, and plan paths to complete their mission successfully, all the while operating in uncertain, dynamic, and complex environments. So there are some examples where we have a UAV that's monitoring a crop field and it has to decide which crop to look at more carefully. Then how to pick up an object, how to identify the object, and finally exploration in completely unknown and possibly challenging environments such as this tunnel. So in today's talk, I want to discuss how we can get into this reasoning mindset for drones and allow them to move in an intelligent way to gather most useful information using onboard sensors given the current state of the environment. And specifically, I want to talk about how we can integrate new learning-based methods or AI and this idea of informative path planning, which is adjusting these decisions on the go during a mission to complete tasks such as these ones. So here's a more specific example of a decision that might need to be taken. So let's say we have this UAV and we deploy it in an unknown crop field. So at the beginning of the mission, maybe the UAV flies a coverage-like pattern to explore the environment, figure out where the crops are. But let's say at a certain point in the mission, it detects something. For example, a cluster of weeds or something strange happening, some kind of anomaly. And now we need to decide, do we want the UAV to stay where it is to collect more measurements, potentially at a lower altitude and higher resolution? Or should the UAV continue exploring the environment to parts that it hasn't been to yet? So these are the kind of trade-offs we want to solve. If we have a decision-making scenario, how should the UAV act in order to get the most useful information given its limited mission time? For example, battery constraints. And in the literature, we call this problem the informative path planning problem. So we're trying to maximize the data, the information acquired, given some constraints, for example, on endurance or battery life. So how can we actually do this? Let's build up a structure of an autonomous system to see how this can be done. So as I said, let's say the UAV is equipped with a sensor, for example, an RGB or a depth camera, which we use to take the measurements. And then during a mission, we perform mapping. So we take these measurements and we project them into the environment, for example, as we'll see in a 3D environment, and we continuously update the map. So we have an idea of what is the current state of the environment. And here we might also have information from previous missions or a prior that we can add, or we can just assume an unknown environment completely. And then this is the interesting part. So during a mission, we have this map, and from it we can extract the potential information that the UAV would acquire should it execute a potential trajectory. So what the planner does is try to produce optimal trajectories based on a given objective. For example, identify certain crops in the field or map certain parts of the environment more closely. So this is all done online during the mission. So we try to close the loop between action and perception. So we want the UAV using this map to be able to react to what it sees online and execute autonomous missions. So my research specifically focuses on using new AI learning-based methods to solve this problem. So here is a broad overview of what my research covers. We have, maybe you've heard of these terms, reinforcement learning, active learning, neural representation, and large language models is a recent research area. So using reinforcement learning briefly, we want to train a AI model, a neural network, to figure out how to solve this decision-making problem, so how to find the next best actions. Here you can see it applied to a swarming application where the UAVs need to learn how to collect measurements of a field. Then we also looked at active learning, which is, we'll go into this in more detail, how to extract useful training data for training an AI model. So we know that AI models require a lot of training data, for example, labeled images to work. And here we want to use the UAV to collect useful training data for a neural network. And we apply this to this kind of urban environment, as we'll see in the examples later. Then we also look at neural representations. So this is basically using these very compact AI models, simple neural networks, to represent complex scenes. So if we have a set of images, we can essentially train the model using these images, and then the model will tell you what it would see if I put the camera in another place. So it has these capabilities of like hallucinating, given all the information that it was trained on. And we use this to do next best view planning. And then finally, we're looking into now using language models, integrate them into this active planning framework. So for example, here you can see a plant in the rectangle, and the idea is like you tell the UAV or a robot in this indoor scenario, go to the plant using just language, and the UAV should be able to do that. So in today's talk, I want to talk about the first three topics due to time constraints, and also because these are the ones that we worked more closely in. So let's start with reinforcement learning, and specifically how we can use that for informative planning. So the main idea is actually quite simple. What we want to do is learn from data. So we have a neural network. So this is a very compact model, a deep learning-based AI model we see on the left. And this model has some parameters inside of it. And then we have a simulation environment. So here we have a UAV and a realistic simulator, and we simulate many episodes of the UAV collecting data in a terrain monitoring problem with different terrain distributions. And then by looking at what happened in the simulator, we can optimize the parameters of the network. So this is what the diagram is illustrating here. We have, we extract a training data, and then the network learns to predict if I'm in a particular state. I can just do a forward pass, I can deploy my network, and I know what's the next best thing to do because I looked at the simulation so many times and I learned the next best actions. So why would we want to do this? Well, because it's very computationally efficient. This network is quite compact, and all the information about decision-making is stored in the compact model. You can see the image shows how many parameters it has, but a forward pass can be executed online during a mission. We'll see that in the results. Otherwise, if we adopted a model-based conventional approach, we have the UAV, and then we have potential places it can go. And for each of these places, we need to simulate data collection and use exhaustive search. Whereas with the neural network, we can just look at the state and it tells us, okay, the UAV should do that. For example, move to the left or move to the right. We don't need to think about, okay, what happens if I move up, down, left, right? All this information is encoded. So here's some brief results of how this approach performs. So on the left, we compare it against different state-of-the-art baselines. We have a sampling-based approach, Monte Carlo tree search. In the purple, we have coverage, which is like a lawnmower strategy, quite simple, what you would do heuristically, and random motion. And then on the right, we see a runtime comparison. So how long do different online planning algorithms take to run? So here we have the state-of-the-art Monte Carlo tree search and also the CMAES, which is an evolutionary optimization routine. So this kind of iterates and finds the best solution. And we can see that the reinforcement learning-based approach reduces the map uncertainty on the y-axis quicker, so how certain we are in the environment, but also significantly speeds up. And this is because, as I said, it has this compact neural network, and the deployment of it is much more computationally efficient than actually using model-based approaches like the other two. So we kind of validated that finding. And then moving to real-world applications, we also tested how this does with real-world data. So we have this UAV, it has a thermal camera on the bottom, and we collected a thermal imagery of a field close to a Bonn. And you can see the red is the areas of higher temperature, and the bluer is the colder areas in the field. So this is an orthomosaic that was stitched together. And then we compared how the reinforcement learning-based approach compares against coverage. Coverage is a zigzag type of pattern, like your typical lawnmower. And we can see we defined the objective, have the UAV map the red areas, the warmer areas, as quickly as possible. So this is how the approaches perform. This is the uncertainty reduction on the y-axis of these hotter areas. And we can see that uncertainty reduces much quicker using our approach, rather than the coverage, because once it has explored the environment, the UAV can stay on the hotter side to collect more measurement here. And in a real-life use case, this would be practical for like a farmer that wants to know about information about plant stresses. So the UAV can adaptively focus on hotter areas. And we can also confirm this by looking at this trajectory. So you can see using the reinforcement learning-based approach, once it has sufficiently explored the environment, the UAV stays on the red side to collect more measurements there, which is what we would expect. Then we also extended this approach to a swarm, a team of UAVs. The idea is quite similar. So here we have downward-facing cameras. We're still looking at a field. Here you can see some real-world data that was collected actually during my PhD of sugar beet fields. And we wanted to map weeds in this field because the data that we have, it's open source. You can have a look. It has sugar beets, and then certain areas of the field have weeds. So the idea is let's have the swarm map the weeds as quickly as possible because these represent infestations. So why is the decision-making problem more challenging here? Well, obviously, if we combine the UAVs, we not only need to decide where to measure next, but also how to cooperate and also replan efficiently. So we developed an approach without going into too many details that was similar. So we have this network in the middle, we train it in the simulator, and we deploy it. And the key innovation here from a research point of view is that we use this new algorithm called counterfactual multi-agent policy gradients. It's quite a mouthful, but the idea is quite simple. We're trying to figure out how much each UAV contributes to the overall mission, the goal of the team. And then we nudge learning so that that agent can improve, so that cooperation can be more effective. And the interesting here is actually that this COMA approach was developed for these standard RL setups. Like it was actually designed for a StarCraft game, a video game, but the innovation here was to deploy it in this multi-UAV setting. And briefly at the results, again, here we can see the map uncertainty on the left in terms of the weeds, and on the right, the accuracy. And we compare against different baselines, including state-of-the-art information gain strategy, again, the coverage thing, and the random movement. And we can see that we get improved coordination because we reduce uncertainty quickly and also get accurate classification as measured by the F1 score. So that validates the approach in practice and motivates the use of these learning-based strategies. Now, here is another extension of the algorithm. So in a more recent work, we also use reinforcement learning, but now we want to plan in 3D environments, for example, orchards. And the tricky thing here is that orchards have obstacles because there are trees and the UAV needs to figure out how to move around the trees. And similarly, we had a similar problem where we want to map points of interest. So in this case, the fruit. So how can the UAV map these fruits while also avoiding obstacles? So we integrated our system basically in a semantic segmentation pipeline. So this is a computer vision model which is able to detect the fruits. And we innovated by proposing a new dynamic graph action space. So what this project did is design a dynamically adjusted graph which represents where the UAV can go. And then as we collect information, we change the branches of this graph or like the nodes to account for the obstacles. And in this way, cater for the fact that we don't know where the obstacles are in advance. And then we updated the graph. So if we see a fruit, we added a potential high information gain there to encourage the UAV to move to that point. Oh, so I also have a video from our realistic simulator. So here we can see the UAV moving around. It's not crashing into anything, so that's good. And it's stopping briefly to replan, so to run the planning algorithm. And it does try to adjust the camera towards the fruit that it sees. As you can see on the right, that's the computer vision output. So this is still to be tested on a real-life platform, but typically we are pretty happy with getting it integrated in a full pipeline that also has the computer vision output and being able to run this on a with the realistic dynamics of the drone as well. So I want to move to the next topic, which is active learning. And here we're going to focus a bit more on the vision side of things. So let's start with the basics of AI for sensing and perception. So typically this represents the state of the art in computer vision for semantic segmentation. This is a key technique which hopefully you might be familiar with. So what a semantic segmentation model does is it's a neural network. It has an image on the left. So this is the input, just your regular RGB image. And then it has these layers in the middle, which look at certain parts of the image, the neighbors, it performs convolutions. And then the output, after performing all of these operations, these layers, the vertical lines, we get an output, which is a per pixel segmentation, which tells us what each pixel in the image is. So if you look closely, the red are the pedestrians, for example. The green, I guess, is the buildings. The purple is the road. So a good segmentation network will be able to really fine-grain separate everything in the image based on categories that we give it. For example, human, road, so on. So we have really good models for this these days. Maybe you have followed developments from Facebook, for example. But the major issue that the community is trying to address is the lack of training data, because these models really depend on many correct images if you want to train them in a supervised way. So you have to have a data set which has RGB images and correct segmentations, and then the model can learn how to predict. So this is quite a bottleneck because getting labeled data is tricky. Often, if you have data, a human needs to sit down and actually label per pixel. So we had students doing that, for example, in some projects where they're just sitting and annotating everything pixel by pixel. And this is obviously very time consuming and also really boring. So the idea is, can we do better by using autonomous UAVs to get training data for human labeling? So we want to address this major bottleneck. So how can we do this? So let's try to build the pipeline again. So the key idea is we want the UAV to collect useful data for training such a model. So again, let's assume this downward facing scenario. We have a UAV with a camera pointed downwards. And now what we have on board is this neural network. This is the cone-like thing here. And during a mission, the network takes an image and then gives us the semantic segmentation. That's this per pixel thing, but also the uncertainty. So the uncertainty is the image on the top. And the higher areas mean there's more uncertainty there. And this is a key aspect of the algorithm. Then, given these images, we assume that we have a perfect localization of the UAV, so we know where it is, and we project the images onto the ground to build a map. So this is the mapping component. And then during a mission, we plan paths for the UAV to collect useful training data. So here, the key idea is to use the ideas from active learning. So what does that mean? We want to collect uncertain images because they represent hard examples for the network. Because if there's high uncertainty somewhere, it means there's low information. Therefore, these images are useful when we add them to the training dataset. If we have high confidence or low uncertainty in something, we don't really have to label them because the network is already pretty good at those examples. So the high uncertainty images, therefore, are most informative or hold the most information value when we add them to the training set. So the UAV collects these images based on the uncertainty, and then the collected data, we take it and we label it. And here we use two sources of labels. So we have a human, and a human annotates very sparse labels. And then we also actually use the fact that we have a map in this process of self-supervised label generation. So because we actually built a map online, we have the insight that we get some of the pixels for free, so we can add them to our training process. So this basically bridges the gap between current semi-supervised approaches and also the informative planning pipeline. And the main idea here is we hope that by collecting images in the smart way and also by using these two sources of labels, the human and the map, we can significantly reduce human labeling effort in active learning for robotic vision. So let's see whether that actually happens. But before, I want to show some visuals so that this becomes more concrete. So for this, we use this dataset ISPRS Potsdam. It's a very interesting dataset because it contains semantic segmentation. It's a large orthomosaic of urban imagery above the city of Potsdam. But we also get a very carefully annotated pictures here. This is the ground truth in the second column. So we have trees, buildings, cars, everything top down collected by a UAV. So we want to test this algorithm on real world data. So here I want to demonstrate first an example of this sparse human labels. So that's the bottom stream. What do they actually look like? So from left to right, we can see the input, the RGB image, the ground truth, the prediction by the network. We can see it's not that great here. Then the sparse labels that the human needs to label. So this is the queries that we ask the human. What is this? Is this a car? Is this a road? And the uncertainty. So we can see that we guide the human to label highly uncertain pixels in general. This is the general trend because the network, this is the only way the network can improve by actually asking the human to label areas of high uncertainty. So the human will therefore label all of these sparse labels. And meanwhile, for the pseudo labels, this is the one that we get through the map. This is without human involvement. And over here, what we want to extract is things that are very certain, because we do build this map online. We take certain stuff from the map, which we get for free. So that's zero effort for the human. And then we ask the human to for input in highly uncertain areas so that it can correct errors in the network. So this is a visual of what these two streams of data in the framework actually look like, and the kind of data that we're working with here. So here is an example of where we actually show the benefits of using this framework. So don't get scared here by the figure. It seems like a lot of information, but it's actually quite easy to interpret, because on the bottom we have, we plot basically the number of pixels that are labeled by the human and as a percentage of the total image. And then on the y-axis, we have the neural network performance. So how good is the neural network in doing this task? So therefore, we want to look at curves which are to the top left. That means human has to label less, but performance is very high. So everything on the top left corner is indicated by better. So that's basically how to interpret these curves. So in the different colors, we plot basically different human labeling budgets. So we have 100, 500, 2000, 1000. So this is the amount of pixels the human has to label. And then on the dashed lines, we see what happens when only the human is labeling. And on the dotted lines, what happens when we also add these pseudo labels. So that is the full approach, the semi-supervised approach. And we can see that adding pseudo labels basically pushes the curves to the top left. So that means better performance. So therefore, adding the pseudo labels and using the complete framework actually improves performance. And the interesting here is that our approach closes the performance to a fully supervised planner, which is on the dashed line. So that's asking the human to label everything. If we do the calculations, we can see that we reach the same performance with only 0.6% of the human labeling effort. And this is quite significant because we saved so much work for the human by introducing these different sources of labels. Now the human doesn't have to label every single pixel, but by using this combination of pixels and the pseudo labels, which we get for free in the map, we can drastically reduce human labeling effort by as much as that. And then we also do a similar experiment to compare the full approach, so the semi-supervised approach, without asking for any input for the human. So on the dashed lines is what happens when we only rely on the map, so the human doesn't do anything. And the solid lines indicate different budgets when the human is actually in the loop, so the human is providing input to this whole process. And we can see that with the dashed lines, performance stays the same, even when we have more images, when we just use the map, whereas we actually can improve, as shown by the curves being on the top, with the human. And this is because when there is an error, we actually need the human to correct it. Otherwise, the error will just stay forever in the neural network system. So this experiment basically validates the fact that unless we have a human actually providing inputs, we can't improve because there's an inherent limitation by the lack of knowledge and systematic prediction errors. So to recap a bit of this section, we introduced an approach for improving networks, collecting useful images to improve networks by bringing together these ideas from computer vision on how to generate these labels and showing that the best thing to do is combine the human effort for highly challenging pixels and also use the fact that we have a map that the UAV is built. And then finally, I want to move to the mapping side of things and how to use neural representations. So for this application, we're going to consider a slightly different problem setup, but we'll connect it to the UAVs in an exciting experiment in the end. So what we do is, let's say we have a 3D object and we want to reconstruct it. Now we have a camera and we can put it in different positions around the objects, right? And we want to solve the problem of next best view planning. So how should we iteratively put this camera to get the most information as possible out of the object? So how do people do that? So in literature, a common approach is to rely on such map representations. For example, a voxel-based map or a surface or mesh, something like this to plan the next best action. So we have partial maps and we complete this mesh iteratively. But the main problem of doing this is that using such large models becomes very difficult if we want very specific high resolution information or we have very large environments. So the main idea here, what we try to do is to consider neural representation approaches, which are based on neural radiance fields. So neural radiance fields, or NeRFs as they're popularly called, is a way of training a very small, lightweight network using 2D images. So here in the black, you can see images that are taken of this drum set, and the network actually encodes everything that we need to know about the scene. And then if we have this set of images, we execute the optimization process, and a NeRF actually learns how to represent implicitly the shape. So that later we can actually ask it, what would you see if we put the camera there? Here's a video to make this clear. So we have some observations to the images, we train our network, and then we can simulate even a video like this one. So this is a quite exciting new development in the vision community being able to do things like this just from a partial set of images because the network learned how to interpolate. So the main idea is to use this because it's compact and it's also very detailed. As you can see, this is a very high resolution rendering of the scene. So how can we apply this to our problem of selecting the next best views? So first we can sample some potential candidates around the object. As you can see, these pyramids, so potential places where the camera can go. And then we have a network. So this is this neural radiance thing. And we ask it, so what is the uncertainty in the rendering when you put the camera in different places? So just going a bit back, if I have this kind of rendering, how confident are you in what you see if you were trained on these images? That's what we're trying to ask. And here, just like in the active learning problem, remember, uncertainty tells us something about information, because high uncertainty means more information is there. So we pick the most uncertain image, we put the camera there, and then we do this process basically iteratively. So based on the uncertainty of the neural radiance field, we guide it to collect information in the next position. So we evaluated this approach on a dataset of shapes called the DTU, a DTU dataset, and we wanted to investigate what is the benefit of using this uncertainty in the way I just presented. So the thing about DTU is that it had fixed camera positions already, so we're not free to move the camera around. So it's quite a restricted first experiment. And we compared against maximum view distance in green, which is a coverage-like approach, which basically says, okay, my camera is here. I want to go to the opposite place because I haven't been there yet. So it kind of heuristically tries to separate the views. And then we also have random, which is just moving the camera around randomly. Here we can see a slight improvement in what is on the y-axis, different image quality metrics. So how good are the images in terms of signal to noise ratio, for example. And we see that the approach performs better. But if we actually give the camera freedom to move, for example, in a simulator, we actually perform a lot better because now the camera is free. We have more flexibility about where the camera can go. And then the differences basically become more pronounced. So this is what we can see in the video here. This is one image of a car that we imported. We can see maximum view distance, random, and our approach. And we can see by looking at the pyramid, so this is where the algorithms allocated the views with the limited measurement budget. We can see more views in the front of the car because the front of the car has a lot of details, the lights and the hub and so on. So you need more images here to be able to reconstruct it in a higher quality way. So if you look closely, especially between random and the uncertainty-based approach, there's a clear difference because it's completely blurry. We don't have enough images here to be able to reconstruct it in a very sharp way. So in another work, just to briefly highlight the idea here, we also included semantics in this. So now we don't want to just reconstruct an object. We have some multiple objects. Here's a random simulation. We even have a plane with a sofa and all the objects that we could find to make it as complex as possible. And let's say we have a cluttered environment and we say we want to reconstruct a sofa here. So now we developed a new algorithm that actually enables us to do this by distinguishing the uncertainty from the sofa from the uncertainty in other stuff like chair, car, whatever there is. So on the left, we see what the scene looks like. In the middle, the semantic segmentation. So this is the differentiation between different objects, the uncertainty, and then the objects of interest, which is in this case the sofa. And we can see that as we move through the simulation across the different steps, the sofa has become much more crispy because we guided the camera using this semantic informed approach to collect targeted images in this point of interest. So you could imagine this being useful, for example, in an inspection application where you have a lot of different objects and you're interested in reconstructing something, then you detect it, so you stay here to collect more images. And finally, I want to share an experiment that my student did. So he came from Bonn to TU Delft, and he set up his experiment here in the flying arena. So our flying arena here, you can see, has a drone, and then we have a motion capture system that tells us the position of the drone. And the drone has an RGBD camera, and we want to map the scene by using an approach similar to the one I presented. This one is based on Gaussian splatting, which serves a similar purpose. It's a different approach to radiance fields, but I won't go into all of the technical details. It's the same key idea. We want to cover the highly uncertain parts. So this is the setup: the drone, RGB camera, motion capture system for the localization, and then you put different objects around. And here's a video of the experiment. So the experiment is actually running in real time online on board, and the map can be seen constructed on the bottom right. So the UAV takes an image, plans something, and then over time it can construct the scene. And in the end, you should be able to see the final mapping results. So we thought this was quite exciting because we really moved away from the synthetic kind of environments and into real UAV applications. There are obviously some issues, for example, the quality of the RGB images that are coming from the camera, but it is a step forward into actually deploying this on mobile platforms and getting them to collect data autonomously. So you could do a similar experiment, for example, just focusing on one of these objects or just the chairs, and then we would expect the UAV to fly around, find the chairs, and then stay collecting more images of the chairs. So that brings me to the end of my presentation. I hope I was more or less on time. I introduced the problem of informative path planning using UAVs, so how we can use them for data collection and allow them to reason online to be able to make decisions to collect useful data, not just any kind of data, as in a coverage-like approach. And then I covered some of the learning-based methods that we're working on to solve this problem and try to connect them to UAV monitoring applications. And with that, I'm done, and I'm happy to discuss or take any questions. I hope everything was interesting for you.
Okay, so thank you. Thank you, Masha. Wow, impressive. Let's see, some questions from audience.
Yeah, I think there is.
Yeah,
Nick?
this is Nick. I put my hand up.
Yeah,
Yes.
we can see.
Very intriguing, very good work. Thank you for discussing it with us. We are concerned, I think, in the longer future about being sure that we can deconflict drone traffic, especially in urban environments. And it would seem to me that the learning module you have and using visual for passive sensing and also interlocking the machines with a nav system might be a very good approach toward having vehicles that learn how to avoid each other as they move through an urban environment. Have you thought about that much? And do you think your methods are applicable to that as well?
I think so, yeah. We were discussing a bit with Marilena on the topic of air mobility, and that is something that came up. I think I've seen some work in this direction, but I would have to dig in a little bit deeper to see what are the current obstacles. I think one of the issues that we often have, especially with collisions, is how to guarantee that you will not collide, because these learning-based methods, that's one of the disadvantages. They cannot provide any like hard guarantees. So I think in such a case, you would have to think a bit about also safety. Yeah, those are my kind of initial thoughts.
Very good. Yeah, my concern was mostly vehicle-to-vehicle avoidance, that the vehicle would each be responsible for collision with obstructions, but that in fact sorting out the traffic environment might be exactly what we're up the alley of this method you've got for having a learning model that would also talk to each of the machines and have them and direct their activities to avoid.
Yeah.
Very similar to the way you direct them to take the appropriate images for crop ag inspection, for example. The mutual collaboration seems to be a perfect and very, very real result of your work, a very, very good result.
Yeah, I totally agree. I think this is something where we can definitely explore further. Yeah. And sometimes in the simulation, we actually had we had to, so you know, these methods, you have to give them an objective. So usually for the collision, we give them like a really high cost. Like if you collide, the simulation fails completely, and that it tends to work pretty well, actually. So you try to put this constraint on not colliding. But I think if you have even more agents, it becomes very, very interesting.
Very good. Thank you.
That's a really nice question. Thanks.
Thank you. Thank you. Masha, I was wondering, you talk a lot here on uncertainty now. So uncertainty is quite important. And you say at one moment, if you have a higher uncertainty, so you have more information there, so you need to look inside. How do you measure uncertainty? Just from my point of view to see.
Yeah, let me maybe go to this example so that I can explain. Yeah, there's different ways of doing it. So for example, let's say this neural network, it has different parameters. So one approach is the parameters are like trained and fixed. So one approach is you randomly switch off stuff in the network and then produce a result. And then you change something else, or like you switch off some of the neuron, you produce another result, and then you measure the variance. So that would be one way of, so you kind of like leverage, it's called Monte Carlo dropout, because you drop out certain parts and then you see what happens. And another approach, which is slightly better calibrated, is if you have multiple models which are similar but not the same, and you call them an ensemble, like a group, and then you measure like how different is the group with respect to each other. Because you would expect that if the models are slightly different, that they don't produce very different results if it's very low uncertainty. So this is some of the methods that we have explored, for example, for this semantic segmentation.
Okay, thank you very much. Linda, you have a question.
Yes, I have a question regarding this semantic segment CNA. And is this neural network training on your synthetic data or the data you collected on the simulation?
Yeah, also good question. For this is all the data from the data set, basically. So this is from the Potsdam data set. We haven't looked at synthetic data, but if you look at the way that the network is trained, I think it would be very relevant to also look into integrating synthetic data, because that could remove some of the human effort even further.
Okay, so the neural network was trained on some real data and was labored by partially human and partially with the precise map information.
Yeah.
Am I correct? Okay.
Yeah, exactly.
And next question will be how generic this CNA may be useful for a different scenario. Basically, use your architecture of this neural network for a different application, training on other data, so I don't start from scratch.
Yeah, also good question. We have deployed the same network in different environments with different data sets. So there was, I wish I had the slide now, but there was a data set which is completely different. Like instead of having close, detailed like urban features, it was like a big lake with like some parking lot, like a orthomosaic. So we validated the method in this environment as well, but we haven't looked into like cross-domain applicability. So if you train on one environment, how good it performs on the other one. It's more like we allow the same starting point for all the methods.
Okay, thank you for your answer. This is a great presentation. I'm just trying to thinking the way how to apply certain information on the other projects. Thanks.
Thanks for the question. We also built actually, I think I don't have the citation here, unfortunately, but we built our own simulator as well, like using open source resources. And then we also had the UAV flying around there in like a factory environment and performing the same approach. Because it was also quite important for us to show that this works in more than this urban data set that was open source.
Oh, that's great. I didn't know that. So you build it as well on a computer. Yeah.
Well, we used the open source, but we did take care to like label everything correctly, because you know you have to group the objects like pipes, or it was a factory, right? So buildings, they had to have one label to make it make sense. So we did a bit of tampering with the resources, but not actually designing the UAV model from scratch or anything like that.
No, wow, great. Yes, so I'm sure that interesting field, Masha, that you are working on. So it's quite.
Yeah, there's a lot of overlap. So that's also what we discussed the other day.
Yes. So it's quite advancing. Are there any other questions or remarks or?
Yeah, I have a question. This is Steve from Alpine Vertical. What,
Please.
our mission is to have the UAV be able to land autonomously in an unpre-mapped landing zone.
Mhm.
How far away are we from that capability, do you think?
Oh, I think you could potentially use some of my methods to identify the landing zone, and then for the actual landing procedure, I think it's like a bit of a different question. I have a colleague who's actually working on landing on a boat, like in storm conditions, so that comes to mind. But I think the actual mechanics of that is a bit of a different field. You could integrate it. So you said unknown, so I think that lends itself perfectly to like active sensing methods and being able to find the landing area, and then you would deploy some landing algorithm to be able to land there.
Yeah, I guess mechanics aside, I think that is a separate problem. But in terms of, for example, the slide that you're showing,
Mm-hmm.
what are the times in seconds in order for today's equipment that could be on board the aircraft, so that as an aircraft is coming in for a landing, it's capturing images periodically as it gets closer to the landing zone. Is it reasonable to expect your system to be able to analyze that in real time or
Yeah,
near real
for
time?
sure. Yeah. These models, like for example, here we use one called the RFnet, so we didn't design it ourselves, but they're pretty fast, lightweight models that don't require a lot of processing time that you could deploy in real time. So we do this typical test of like if you have a camera and you connect it to like your laptop and you run the algorithm, then you point at a different stuff and you can do object detection with a different model, so you can identify like laptop, something like this, and that's really fast. Yeah,
Okay, thanks.
I think for your use case, the object detection might be more suitable, because object detection is basically finding, not doing this dense pixel, but finding like, okay, that's a landing spot and that's like a bounding box that represents it.
Right. And you feel that there's complete enough data sets to be able to do object detection on anything that would show up planned or unplanned in a landing zone, for example?
Well, I don't know so much about the availability of that. I think the models should be fast enough. The data, I will have to read up a bit to see what's available. I'm sure that there are some data sets out there. But if you want really robust performance, you should probably use some of these uncertainty ideas to figure out what's unknown and stuff like this.
Okay, thank you.
Yeah, on that part I work with integrating so on helicopter ship. But for example, if you have a nice steady atmosphere, you don't have a problem, so you can land. But the problem comes when you start introducing the wind, the turbulence, and different things, because then the things are changing. So yeah, integrating those together there must be a kind of cooperation, no? Because it must be, you have this neural network, but if you have too much information, you have to select and to not give all the time too much information to the neural network. Now, otherwise will not work. So yeah, Linda, please.
I think one of the things I understand is you have the neural network combined with a decision tree. Am I correct there?
Yeah.
So what specifically about this decision tree you have compared with just a generic decision tree design? You know, making a AI decision can be very fundamental, simple, but can be very complex. What's this decision tree when you're training you segment identification and then you training your network model to make the decision at the same time? That's a great idea. What I mean is, what specifically about this decision tree when you design it, you see its difference or advantage?
You ask me, Linda.
I'm asking.
Yeah, both of us.
Yeah.
So we
I
are
was like,
working on.
I hope
we are
so.
working on this problem. It's a learning process for us.
Yeah.
So at least yes, we are combining it, and then we try to understand when and how to give to the network the points in order to be able to land.
Oh, landing is a very complex problem.
Yeah.
I don't want to drag on that. I think the best way is probably you should do a flyover, then land, unless you're in emergency, you need to land right now. But that's also, you should train your network before to know what's the right spot. Then if you see it in your image, you might make decision to land. So that's a pre-trained that's networking approach. I was just curious to know in the presentation when there's key points mentioned about capability to make a quick decision compared with brute force gradient search. That's definitely cannot compete with your AI neural network decision. But this decision tree you design in your network, what's the specific thing you see there? Just for me to learn. It's a question for Marija.
Yes.
Can you repeat the end of the question?
So in your previous in the presentation you mentioned there's information collection and there's a segment decision, identification. But at the same time, you do decision making in your neural network. So you know, you already give the move forward, move up and down at the same time using your network. From my view, you just combined a different set of neural networks in a total set instead of people usually do one thing at a time. But in this decision neural net you are using, is there any specific they're very unique about yours?
So we had to adapt the reinforcement learning, for example, with this COMA algorithm for multi-UAV, we had to adapt it for the UAV application. So we have to figure out how do we encode like the position of each UAV, because you could give it the like a floating point array of like where each UAV is, but maybe that's not enough information for the network to learn. So I don't remember like the specific, but we explore like the 2D where the one hot where the UAV is, where the teammates are. So a key part of the experiments was actually which features are useful for learning, which is something that we don't know in advance, for at least for this problem.
Okay. I think that if I understand is a decision was more better for uncertainty to make, even with the uncertainty to make the decision. For the design you have. Okay, over. Thank you.
Yeah. So the network itself, we didn't play around too much with the architecture. We kind of looked at like what is used in the COMA paper, and then we use that. But obviously, the input to the network cannot be the same because they provide these kind of like video game information, like which coordinates on the screen and so on. So we have to check how to transfer that to the UAV application, and figure out like the best combination of how to represent the information gain, how to represent the positions. Does it help if we add the history of where the UAVs were rather than also the current position? So those are some of the decisions that we had to make.
Thank you. Over.
Yes.
Thanks.
Thank you. Now we are 5 minutes over the time, and thank you very much, Masha, and thank you very much for being online. We see each other next month.
Thank you so much.
Thank
Thank
you.
you.
Really
Thank
nice
you.
to meet you.
Thank
Excellent
you.
presentation.